Hello fellow skeptics, this is with the name, and this is the second video that I'm presenting on the topic of what's wrong with modern physics and how can we fix it. Again, I expect you to be skeptical, and in this particular video what I'm going to do is provide you with the tools to understand and validate my initial claim that we've missed some basic physics. In particular, this physics has to do with the center of mass. You may recall I used the description of a dumbbell in orbit as a complex object with two masses instead of a single mass. So I'm going to show you how we actually find what the angular momentum, the orbital angular momentum is of that object and other objects, so that you can see how important that particular observation was, that discovery that there was a problem with the center of mass. So with that, let's go ahead and get to the slides. This set of slides is given to indicate how we quantify the orbital angular momentum. All we're looking for here is a description of what the forms are for the orbital angular momentum as we currently use it as a point mass object versus what it would look like if we were to account for all the mass elements having finite dimension. There are many Wikipedia articles and textbook examples of the angular momentum, orbital angular momentum of single and collections of particles. We're just going to limit the discussion here to how we might quantify the orbital angular momentum. In all of these, the vector r goes from the center of curvature out to the center of mass of the objects we're looking at. And the orbital, and it's in a single plane in this instance, where the center of mass, located here at the center of the crossbar between these two point masses, is given by that vector r times the angular rate at which the object is moving in an angular direction. This is a planar representation, two-dimensional object. We'll show what happens when we change it to a three-dimensional representation. But in this particular instance, this is how we currently would find the orbital angular momentum. This is how we do find it for any object, whether it has one mass concentrated here or two separate mass elements located at the end of this particular crossbar of length d. When we look at it as two separate objects, as opposed to a single object, we now have two orbital angular momenta for L1 and L2. We sum those together, and what we find is that we have collectively a perturbation on the center of mass value that we calculated before, but we have something else that's representative of the finite dimension of the object itself. Now, this is the first step in treating what is often called a multi-body problem, where we have 2, 4, 6, 8, any number of point masses, and then we sum those together to come up with the effective angular momenta and other physical properties of that collection. So this is consistent with just looking at a two-point problem. And these are conservative systems in the sense that if it's in orbit and there's no external force like a rocket motor pushing on it, and so that its orbital motion effectively is not being accelerated in any fashion, then what we have is a conservative system, which says that this angular momentum is conserved, it doesn't change, it stays at a constant value. However, there's something else that is not noticed about these by using and sticking with just a center of mass approach. If we were to take that and reconfigure this as a three-dimensional type of problem, where again, this is at right angles now to the vector r, you can see that when this system rotates around so that the masses are aligned along R, we have the situation that we discussed previously. Now, however, as it continues to rotate past that, where the connecting rod is aligned with the vector R, what we see is that we come into a situation where it's perpendicular to that vector. In this instance, when you calculate the orbital angular momentum, there is no perturbation. It's just the center of mass value given here. So if the object continues to rotate, just as the Earth rotates around its axis, as the Earth revolves around the sun, what we have is a fluctuation then in the orbital angular momentum as it goes from a maximum when it's aligned to zero when it's not aligned, when it's perpendicular. This has consequences in that because the orbital angular momentum is what we call conserved, doesn't change, something has to change. And what that something is, if L is constant, then we have both the angular rate omega and the distance r are the only variables that we might have. And what happens is, as r fluctuates, then omega has to change. In other words, the angular rate, the orbit of this thing. And if omega changes, then r also is affected. So what you have is r oscillates back and forth here at the rate omega square, which is the rotation rate of the system. And the angular velocity also oscillates slightly back and forth around that same point with that same rate in order to keep that quantity L constant as the thing rotates back and forth. Those fluctuations have never been seen before or talked about. The fact is that for man-made objects like satellites going around the Earth, these variations are in the order of millimeters of radial change and microradians in terms of the fluctuation in the angular rate of the object. But the object is fluctuating. You could say that if we could measure it, the Earth would be fluctuating ever so slightly, though its relationship to the sun, again, it's a small object relative to the sun, so these would be very small variations. I don't even know that we could see them or measure them, but very possibly there is some 24-hour cycles that we have seen and attributed to other sources that in fact is a result of this fluctuation that we have not paid any attention to, or even known it exists, as a matter of fact. So, if we take a look at this as a single object, just a sphere, again, the dimensions are the same, only in the first instance, what we have is that all mass is considered concentrated at the center of the object, and we get the same exact center of mass. If this mass is the same as the mass of the dumbbell, then if we consider the mass here to be the same and concentrated at the center, then we get exactly the same orbital angular momentum. However, if we go back and look at the formal definition, and this is just to show that we have a first principle formal definition of what the orbital angular momentum would be, where these are vector quantities and these parallel lines indicate we're just taking the magnitude of these. This is the momentum given by mass times, in this case it would be speed, not velocity. What we have is this reduces, this complex system for a point mass reduces to our center of mass value that we've gotten before. However, if we look at this object, in this case I'm looking at it as having a constant density, so that we have an incremental mass volume there with an incremental mass element in there located somewhere off the center of the object at a new distance, and its distance is r prime from the center of rotation. We now have an incremental angular momentum associated with that mass element given by this expression. And when we look at all of these mass elements, sum it up using calculus, what we find is that we have a new, we have a center of mass value with a new perturbation that's representative of the dimensions and characteristics of this object, as opposed to the way it showed up for the dumbbell itself. However, there's more to it. This is a stylized representation of the moon going around the Earth, even though the moon doesn't precisely go around the Earth. In terms of our modeling, this is what it looks like. The moon is tidally locked to the Earth, meaning that as it goes around in its orbit, one face always points towards the Earth. But if you look at this is actually a single additional rotation of the moon around its axis, its spin axis. It's spinning on its axis once every orbit, which is given by omega here. As a result, we have what appears to be a rotation where we claim that the moon has no rotation. This is true for all objects. The Earth going around the sun, it spins on its axis every 24 hours. It has a period around the sun of 365 days, but it also has a perturbation of a single extra rotation once per orbit of the sun. It's there for all finite objects that are in orbit. If we look at this then, and take a look at our original calculation on the orbital angular momentum for the sphere, including perturbation, we can rewrite this, the same expression, rewritten algebraically, to show two terms. One is the center of mass term, and the other is this extra term here. That is the perturbation, and that represents that intrinsic single rotation, because here we have the same angular rate around in orbit for both terms. So that's the intrinsic. I call it the intrinsic. All objects, all finite objects have it. If they're moving in an arc, they have an intrinsic component of their angular momentum, something which we have heretofore only attributed to non-classical objects as quantum, such as in quantum objects. So, what can we say? All finite non-point objects have an intrinsic angular momentum, no matter how brief the angular motion, and no matter what the intrinsic rotation of the object. Intrinsic in this case being like Earth's rotation around its axis in 24 hours. This extra intrinsic angular momentum is an orbital momentum component, and it's independent of the rotation rate of the object, except as the object is not uniform in mass distribution. Then there would be these fluctuations that you would have in the value of the total momentum of the object. It would fluctuate, even though it may stay constant, as in orbital or central force problems. What else can we say? We've come very close to identifying that this intrinsic element exists. In the way we look at various types of objects in orbit as multi-body problems, and we've come very close to recognizing it. And in fact, other ways of looking at the momentum of objects in motion, mostly concerned with how the object behaves as it spins around an axis that passes through its center of mass and spins around that axis. We identify something called the moment of inertia of the object, and if we multiply that moment of inertia, which is characteristic of the mass distribution, shape, and size of an object, we multiply it by the spin rate of the object, and we get a spin angular momentum. But there's another factor with that we can find the same an angular momentum of the object spinning on an axis parallel to that one that goes through the center of mass, if that axis is, say, passing along the edge of the object. However, if we go ahead and take that parallel axis and move it to the center of rotation of that vector r we've defined before, so it now is located at the center of angular motion of the object, that same parallel axis theorem in fact gives you exactly what we do and what we find when we use the exact expression for the orbital angular momentum. We've alluded to it. We recognize that something is there, but we haven't identified it actually with looking at the first principles orbital angular momentum and the fact that it can have fluctuations in it that we have not seen. We may have measured it, but we don't know that we've measured it. So what else can we say about this? Well, in Newton was stimulated to find solutions to what was called the Kepler problem, which is an orbit of a planet around the sun. And he was motivated to find a mathematical description of what Kepler had observed. But this is also the only exact solution that we've been able to find in quantum mechanics, which is the hydrogen atom, or an ionized helium atom, and so forth. It's the Kepler problem. It has a single central mass element and a single orbiting object, whether it be an electron orbiting or a planet, or whether it be a proton at the center of the sun. It's called the Kepler problem, and we've been undercounting the orbital motion of these objects, even though we've talked about how the orbit changes with changes of eccentricity. We've never really connected the dots. Again, a lot of dots, no connection. The rotation of an object about its rotational axis does not affect the orbital eccentricity and orbital shape, except if it has an intrinsic angular momentum. There is an implication here that subatomic particles with intrinsic angular momentum are likely all finite objects. I'm not sure that's a true statement, but it's something that you could test. We lack the tools for being able to identify many of the attributes of subatomic particles. We know that their behavior is distinctly non-classical in certain senses, but we lack tools to be able to actually probe what some of the differences are in these objects themselves. This is just another, you might say it's the orbital angular momentum and this intrinsic angular momentum definition is another arrow in the quiver of physicists to be able to understand more completely what's going on in these quantum systems. So, just to reiterate, the point of this was not necessarily to show exhaustively what the orbital angular momentum or any angular momentum might be. It's to show that reliance on the center of mass carries risks. And the risks have been that we've omitted and overlooked certain things. Now these issues will come back in a big way to haunt physics. And that's what the next video will show. That the center of mass, in fact, has led us, at least is the major issue, the use of it, has led us to do and make certain assumptions that have led to errors in modern physics. And with that, thank you for watching. This is Luther Name, and I'll see you in the next video.